Okay, so it's pretty well established that our surface is heating up. When talking about global warming, when talking about the increase in average temperatures, we're actually talking about the average surface temperatures of the Earth. We're talking about what's happening down here. However, our atmosphere is actually made up of several different layers. The layer down here that we're dealing with is what is called the troposphere. That's where our weather's at, that's where we live at, and our troposphere has been warming up. However, believe it or not, we also monitor conditions in the layers above the troposphere, and the layer directly above the troposphere is what's called the stratosphere. And what's actually been happening is, while we down here in the troposphere, and let me actually draw this. So here's the surface. And let me, whoops, sorry about that. And roughly about 9 kilometers above the troposphere is this boundary called the tropopause. And above it is what is called the stratosphere. So we're down here in the troposphere. And then the layer above us is what's called the stratosphere. All right. So what's actually been happening over the last 140 years is the troposphere has seen substantial warming. Temperatures are going up down here. It's getting hotter down here. However, if we actually go up into the stratosphere, which we actually do monitor by the launching of weather balloons, by aerial reconnaissance, by satellite data, what we've actually noticed is that the stratosphere has actually seen cooling. The stratosphere has actually seen cooling. So while down here, near the surface of the Earth in our troposphere, temperatures have been going up, temperatures have actually been going down in our stratosphere. Now, why would we call that the smoking gun of climate change? Well, the reason why we would call that the smoking gun of climate change is that something is happening that is keeping heat trapped in the troposphere. Because something is happening that's keeping heat trapped in the troposphere, that heat does not rise into the stratosphere. So the heat stays down here, keeping us warmer. And because it stays down here, it doesn't go up into the stratosphere, and it makes the stratosphere colder. Well, what could that something be? Well, there's actually two possible answers. The first answer is kind of the obvious answer, which is greenhouse gases. We have these little greenhouse gases. And I'll just label them GHGs. And we know that our planet gives off long-wave radiation. Our planet gives off long-wave radiation. So that's pretty well known already. Well, those greenhouse gases absorb that long-wave radiation, preventing it from further rising into the stratosphere. As a result, less heat is making it into the stratosphere, and because less heat is making it into the stratosphere is cooling down. So that's one of the two main causes of stratospheric cooling. Greenhouse gases being increasing in concentration down here, trapping heat down here. But what is the other cause? Well, the other cause has to deal with something that is near and dear to our hearts. Why? Because it prevents us from burning to death. I'm talking about the ozone layer. So I've very briefly talked about ozone in this class, and most of what I've talked about in ozone in this class has dealt with the troposphere, has dealt with down here near the surface of the Earth. Down here near the surface of the Earth, ozone actually behaves like a greenhouse gas. It traps in heat down here, preventing it from escaping. However, we have here down here near the surface of the Earth a teeny tiny little bit of ozone. We don't have a lot. So its effects are really very, very small when compared to carbon dioxide or methane or any of that other stuff. Ozone's impact down here near the surface of the Earth isn't really that big. However, higher up in the atmosphere, specifically in the stratosphere, ozone is a very big deal. And the reason why it's a very big deal is because ozone has the property that it actually absorbs ultraviolet radiation. So ultraviolet radiation from the sun, which is very high energy, has the ability to cause burns, trigger mutations, and can even cause cancers, is making its way down to the surface of the Earth, and it's getting absorbed in the ozone layer, preventing it from reaching the surface of the Earth, protecting us from it. So the ozone layer protects us from all of this stuff. Well, here's the thing though. Just like when the ground absorbs sunlight, or when the atmosphere absorbs sunlight, or when anything absorbs sunlight, when this ozone absorbs sunlight, it heats up. As a result, that is a heat source for the stratosphere. Well, I'm not sure if you've heard this or not, but over the past roughly century, we have seen a substantial decline in ozone concentrations. The main reason why is because of these things called chlorofluorocarbons. Try saying that 10 times fast. Or CFCs. Basically, what chlorofluorocarbons are, they're these chemicals that contain carbon, chlorine, fluorine, and hydrogen. Hence, they're called chlorofluorocarbons. These things have been seen as sort of like the miracle gas for people down here on Earth because they don't have any health consequences. They were seen to not really harm air quality at all. And yet, for the longest time, we used them in everything from spray cans, like that right there, to refrigeration, to air conditioning. Chlorofluorocarbons have been sort of our miracle down here. Well, here's the problem. Once these chlorofluorocarbons get released into our atmosphere, they float their way up into the stratosphere, and through a chemical reaction that I'm going to talk about in the next few minutes, they break ozone molecules up into molecular oxygen and elemental oxygen. So they basically take that third oxygen atom and break it off, leaving you with just molecular oxygen. Well, that molecular oxygen is not as absorptive of ultraviolet radiation as ozone is. So what that means is that we now have less ozone in our atmosphere, and therefore less ultraviolet radiations being absorbed, more is making it down to the surface. And that's bad because not only is that going to give us more sunburns, that could actually cause tremendous amounts of cancers, mutations, and not the kind that are going to turn you into the Incredible Hulk, the kind that are going to kill you. So CFCs can originate from all kinds of things. As I just mentioned, aerosol spray, refrigerants, even cleaning solvents contain CFCs in them. So all of these things contain CFCs in them. And as I mentioned, they were kind of like the miracle gas. They had very little negative environmental impact down here near the surface. They didn't harm air quality. They weren't harmful to breathe in. So they were good for the longest time until we found out that they were eating apart our ozone layer. Now, that being said, we realized in the 1970s and 80s that this was happening. And when we realized that this was happening, that our ozone layer was being chewed up by these CFCs, we realized we had to do something about it. I'll mention that something in a few moments. The something that we had to do about it is we had to prohibit the use of these CFCs in the future. So here's what happened. In the late 1980s, there was an international agreement called the Montreal Protocol. The Montreal Protocol was an agreement by the world's top developed nations as well as the big up-and-coming nations. They got together and they made an agreement. No more CFCs. We realized that if we continue using CFCs, we are going to destroy our ozone layer, and that's going to make this planet uninhabitable. So no more CFCs. Well, guess what? It worked. In the last 20 years, our ozone layer has begun to recover. But let me explain basically how ozone depletion works before I get back to that good news. So the way it works is different parts of the world have different ozone concentrations. Higher ozone concentrations are indicated in green and yellow and orange. Lower ozone concentrations are in dark blue and purples. Well, what you actually notice is as you go throughout the 1980s, ozone concentrations over the southern hemisphere, specifically the South Pole, became smaller and smaller and smaller. This is what we actually refer to as the ozone hole. And I'm sure you've heard about the ozone hole before. Basically what it is, it's this patch of lower ozone concentrations that forms over the South Pole in the months of late September and early October. I'll explain why that happens in a moment. But for right now, the ozone hole is basically this hole, this patch of really, really low ozone concentrations that forms over the South Pole every single year in the months of September and October. All right. That being said, that's our ozone hole. However, in addition to the ozone hole forming, another thing that happened that a lot of people began to notice is that overall, globally, concentrations in ozone were declining slightly from year to year to year. The ozone layer was getting a little bit thinner, a little bit thinner, a little bit thinner, a little bit thinner every single year. And so this crisis that we were facing was not just present over the South Pole, but actually present globally. And so that's what ozone depletion is. So ozone depletion is the global decline in ozone. The ozone hole is specifically that area over the South Pole that sees a big decline in ozone every single year in September and October. So why does it happen in the South Pole? Why Antarctica? Why does it happen in Antarctica? Well, as I'm sure you probably know, Antarctica is very, very, very cold. And these colder temperatures make it so much easier for chlorine to split off from those CFCs. And so that's the first step that's necessary. You need really, really cold temperatures. The second thing you need is you need the temperatures to be so cold that the scant amount of moisture that's present in the stratosphere actually freezes into what are called polar stratospheric clouds. They're very, very beautiful clouds, but they kind of help act as a catalyst. They help act as a catalyst to split off that chlorine from the CFCs. So now we have these chlorine atoms that are breaking off from our CFCs. Polar stratospheric clouds are helping make that happen. And then those chlorines that break off then begin to wreak havoc on ozone molecules. And they begin to break off with the help of sunlight. They begin to break off one of the oxygen molecules from ozone. Now, why does this happen in September and October? Well, believe it or not, September is actually the coldest month in Antarctica. The reason why is because while we're up here basking in summer in June, July, August, and September, Antarctica has been in darkness for roughly 6 straight months. And so the temperature has gotten colder and colder and colder and colder. That allows these polar stratospheric clouds to form. That allows the chlorines to break up very easily. But that's only 2 of the 3 steps. The step that's needed to break up the ozone is sunlight. Well, up until this point, it's been getting colder and colder and colder because the sun hasn't been out. And then comes late September. Then comes what we call the autumnal equinox. If you are at the South Pole, on that day, the sun rises for the first time in 6 months. And then boom, that incoming sunlight kicks off the reaction that breaks apart ozone. It kicks off that reaction that breaks apart ozone. So again, you need 3 things to happen. First, you need cold temperatures for chlorine to break off from the CFC. You need polar stratospheric clouds that help speed up that reaction. You get both of those things in late September, and then you need that first crack of sunlight. And that causes the chlorine to react with the oxygen in the ozone, breaking off an atom of it, and boom, there goes your ozone. So here are some of those polar stratospheric clouds. They are way above the surface of the Earth, way above the flight level that you would ever be on if you're in an airplane. They are 50,000, 60,000, 70,000, 80,000 feet above the surface of the Earth. So they're way up there. And they're very beautiful and they're very nice to look at. But it is them combined with CFCs that break apart our ozone layer. So with that being said, we now have 2 things happening. So we have ozone declining, and as I mentioned earlier, when ozone declines, that means there's less ultraviolet light being absorbed. That cools the stratosphere down. The second thing is you also have greenhouse gases down here in the troposphere. Those prevent heat from the Earth, that long wave radiation coming off from the Earth, from actually making it into the stratosphere. So now you have less ozone to absorb incoming sunlight, and you have less long wave radiation from the Earth going up due to greenhouse gases. Those 2 things put together result in a colder stratosphere. And that is why it's considered the smoking gun, because both of those things, that decline in ozone and the decline in outgoing radiation because heat is being trapped by greenhouse gases, both of those things are caused by human activity. So the answer, in short, is we are the ones that are cooling our stratosphere. We are the ones that are cooling our stratosphere. And so as greenhouse gases, specifically carbon dioxide, methane, nitrous oxide, and other greenhouse gases go up, as we see more of those down here, less radiation's making it into the stratosphere becomes cooler.